Dear students, today we will discuss about the series regulator design or series voltage regulator design. What we are discussed in the last class, we are discussed about the voltage series voltage regulator, and also there is one more regulator that is the implement of that circuit is Christian voltage regulator with Zener diode circuit connected to the regulator output. We are connected the Zener diode at the output of circuit to avoid the changes in the supply voltage. If the changes in the supply voltage occurs, automatically what happens? It will affect on the Zener voltage. If it is affecting on the Zener voltage, automatically output changes. To avoid this one, we are consider this circuit instead of the first circuit. In the figure as it is shown in figure 1, instead of figure 1, we are considering this circuit, Christian voltage regulator circuit. That is, by considering the Christian voltage regulator circuit, to calculate the value of R1 value, if you calculate the value of R2, to calculate the value of R3, and to calculate the value of the other values and C1 values. And these things, some of the values we are considering, and some of the values we are going to calculate for the Christian voltage regulator. That is the design, how we are going to make the design of Christian voltage regulator circuit. To design a series regulator circuit, the Zener diode is selected so that its voltage VZ, the VZ is less than output voltage. The Zener diode voltage should be less than the output voltage. For example, consider I need the 12 volts output, regulated output. At that case, I am going to select the 9 volts Zener diode voltage, Zener diode. If I want 12 or 15 volts regulated output, at that case, I may select less than that one. That is, I want 12 volt. I am going to select 12 volts is a diode. It means it is depends upon a particular condition. A Zener voltage is less, approximately equal to 0.75 times V naught. That is 0.75 times V naught is 75% high of output voltage. VZ should be, that is original diode voltage should be 75% times V naught. That is the case. You have to select depending upon that one, depending upon the output voltage. I have to select the Zener diode. This type of Zener diode you have to select. Either it will be different type of voltage, Zener diode voltage available the, depending upon the specification. The current levels are chosen. The current levels are chosen. IZ and I2 are assumed are chosen, uh, and the resistor values R2 and R3 are calculated by using the Ohm's law, so that the resistor current is much. That is, in this case, we are going to select, and also we are going to consider the input current, that is the I2 current is greater than the bias current of the operation amplifier in the precision voltage regulator. That is, in this case, and one more thing is transistor Q1 is selected to pass the required load current and to survive the necessary power dissipation. That is around, it is drop across the Q1 it will occurs. That is to work. It is also by including that voltage drop, we are going to consider the required load current to pass the required load current. that is to survive the necessary power dissipation, heat sink will be provided for the series pass transistor to dissipate that heat. So the heat sink will be provided. What should be the around? Suppose we are considering in this case, what should be the power dissipation of the uh, voltage across the transistor is? There is the difference between the regulator input and output is the difference between the regulator input and output is depends upon the collector to emitter voltage drop. The minimum level of VCE to keep the transistor operational is known as the dropout voltage. That is, this is usually considered around 3 volts. That is the minimum level of VCE, that is the current to collector to emitter voltage drop. As I considered in the previous case, the total voltage drop occurs across the transistor is VCE into IC. That voltage drop across series pass transistor is 3 volts. Here we are considering 3 volts. And also there is a drop due to the input ripple voltage is the input voltage ripple is around 2 volts. Totally how much? That is here you consider when designing for a given regulated output. Suppose if you are designing the circuit or a voltage regulator circuit, that is the supply voltage must be at least V naught plus 3 volts. What should be the V naught? V naught here is the voltage drop across series pass transistor at the lowest point in the input voltage. What is the input voltage? Input voltage is unregulated input voltage, allowing for a supply ripple voltage of 2 volts. Along with that one, that is 2 volts of ripple, supply voltage ripple is considered peak to peak. It will be added. Total how much? 2 volts plus 3 volts, 5 volts. Unregulated supply. Depending upon how much we have to supply, 5 volts more than the required output voltage we have to supply at the input of as a unregulated input voltage. Suppose I want 10 volts regulated voltage, then at the input we have to supply 15 volts unregulated supply voltage. It means 3 volts drop occurs across transistor, and also supply voltage ripple is 2 volts will be deducted or it will be subtracted totally. Then 15 minus 5 volts will be we are getting totally the regulated voltage exactly I am getting is 10 volts. That is, for example, the power supply at the input should be at least 5 volts greater than the regulated output voltage. And also here sometimes we are considering plus or minus 10% will be added to this 5 volts. That is, this plus or minus 10 volts is added due to the supply voltage change. That is, sometimes this supply or line voltage change occurs. That will be around in terms of millivolts. It will be not considered. Totally 5 volts greater than the required output voltage, regulated output voltage. One problem we will consider on this on this circuit, Christian voltage regulator circuit. Design the voltage regulator circuit to produce 12 volts output. I want 12 volts output with a 50 milliamperes maximum load current. In this case, VZ should be, as I considered in the design procedure, that is VZ should be 0.75 V naught. What I know required V naught is 12 volts. 0.75 into 12 volts. I am going to get 9 volts. The Zener diode I have to select 9 volts Zener diode. Various voltage ranges are available. Zener diode voltages are available. In this case, I need 9 volts Zener diode. In this case, I am selecting 1N757 Zener diode. Its voltage is rating is 9 volts, 9.1 volts. And also selecting or assuming IZ is equal to 10 milliamperes. That is the IZ is 10 milliamperes. Then I am going to calculate R1 value. R1 is equal to, as per the Ohm's law, just you see the circuit. See the circuit as I am going to take. This is R1 value. R1 value. This point to this point. What is the voltage? This point to this point. The voltage is this point to this point. The voltage is that is V naught, and from this point to this point is how much? The voltage is around Vz, and I want to calculate the voltage across R1. The voltage across R1. The voltage across R1 to get R1 we have to get our value of R1 according to Ohm's law. R is equal to V by I. What is the current? Current is flowing is in this path is, what is the current which will be flowing? The current which will be flowing in this path is IZ. I am considering the IZ value, and automatically I am going to get the R1 is equal to the V naught by this point to this point, the voltage V naught. Okay, this point to this point V naught minus Vz divided by Iz. From this particular circuit, I am going to consider that is the voltage is R1 is equal to V naught minus Vz divided by Iz. Then total V naught is 12 volts, Vz is 9.1 divided by Iz is assumed or considered for the particular Zener diode. So I am getting 290 ohms. The standard resistance is 270 ohms. Next, for I2 is greater than the bias current of the operational amplifier. In this case, for this voltage regulator, especially for voltage regulator circuits, we are going to consider I2 as 50 microamperes. Then for this one, R3 is equal to Vz divided by Iz. How to consider Vz divided by Iz? Go to the circuit. Again, V by Iz by Iz for R3. Vz divided by Iz. But is in this case, I am going to consider the voltage around this one is, it is from this point to this point, from this point to this point, I am going to consider this point to this point. What is the voltage? This point to this point is Vz. From this point to this point, then again the voltage across R3 is Vz. Okay, the voltage across this point to this point across R3 is Vz. Okay, this point to this point voltage is same, and this point to this point the voltage is again Vz, the voltage, and the current flowing through this one is I2. The current flowing through this path is I2. Okay, it is then for this path to calculate the value of R3. I am going to consider the value of, and chosen the value of I2. Vz is already we are considered, we are calculated 59.1 volts. I2 is 50 microamperes. From this one, I am going to get 182 kilo ohms. Standard value is 180 kilo ohms. Next, to calculate the value of R2, that is, I'm going to get V naught minus Vz, that is point to point, end to end, point V naught minus, I'm going again to, I'm going to circuit again, that is this point, between voltage across R2, voltage across R2 is, there is total voltage from this point to this point V naught minus Vz across R3 is Vz divided by I2. I'm going to get R2 value. I'm going to get R2 value. The same thing I am writing here according to the Ohm's law. From the value of R2 is equal to V naught minus Vz. V naught is the total voltage from point to point minus Vz is the voltage across R3 divided by the current is flowing through that particular branch. Right? 12 minus 9.1 volts. Then I'm going to get divided by 3 microampere. Next, I'm going to get 58 kilo ohms. Standard value is 56 kilo ohms. From equation 3 and 4, from equation 3 and 4, V naught is equal to R2 into I2 plus Vz. That is, V naught is equal to R2 into I2 plus Vz. From equation 3, the value of this one is V naught is equal to R2 into I2. That is, R3 into I2. That is, this is R3 into I2 plus Vz. So R3 into I2 plus Vz. Next, from equation 4, I am going to get R2 into I2 plus Vz. That is R2 into I2 plus R3 into I2. That is, from this one, I am going to get R2 into I2. That is, I am going to get V naught is equal to R2 into R3 into I2 plus Vz. R2 into I2 plus R2 into I2 plus Vz. From equation 4, I am going to get V naught is equal to R2 into I2 plus Vz. Next, V naught is equal to R2 into I2. R2 into I2. What will be the value of Vz? Vz is equal to R3 into I3. R3 into I2. That one again I'm going to write V naught is equal to R2 into I2 plus R3 into I2. Vz is R3 into I2 from equation 3. Then I am going to get the total value is V naught is equal to I2 common in both the sections. R2 into R2 plus R3. Therefore, V naught is equal to Vz total equation. Vz is equal to Vz into R2 plus R3 divided by R. Total equation we are derived in the previous case. Therefore, we are derived. That is automatically. Therefore, at A2 is equal to get this one, the V naught value, V naught is equal to A2 is equal to V naught divided by R2 plus R3. R2 plus R3. Then automatically what happens? What is the value of V naught? V naught is equal to Vz into R2 plus R3 divided by R3. Then automatically from this equation, actual output is 9.1. Vz is equal to 9.1 into R2 plus R3 divided by 180 kilo ohms. Therefore, V naught is equal to 7.9 kilo 9 volts. Supply voltage Vs minimum is V naught plus Vce minimum. That is, supply voltage is I required output voltage is 12 volts and Vc minimum is 3 volts. Therefore, Vs minimum unregulated supply voltage should be 15 volts. And if it is the Vs is equal to Vs minimum plus We are ripple voltage, we are peak to peak plus 10%, that is Vs minimum is total Vs minimum is the supply voltage Vs minimum is 15 volts plus the ripple voltage is 2 volts and 10% line voltage change, that is 1.1 plus plus 1.1 is not into 1.1 plus 1.1, that is I am going to get nearly around 19 volts. That is automatically I am going to get uh, 19 volts. That is the specification for Q1 ECU minimum, that is equal to Vs is equal to 19 volts. That is IC maximum is equal to IL plus IZ plus I2. IC maximum is equal to, that is 50 milliamps plus 10 milliamps plus 50 microamperes, that is 50 milliamps. Totally AC maximum, that is the current should be current collector current of the transistor is 60 milliamps. Power dissipation to the transistor is Vs minus V naught, Vs minus V naught into IC. That is unregulated supply voltage minus regulated output voltage into IC. Therefore, 19 unregulated voltage supply voltage is 19 minus required regulated output is 12 and total collector current is what 60 milliamperes. Therefore, 420 milliwatts. The power dissipation across transistor is 420 milliwatts. From this one, we have calculated all the values. Any doubts related to this problem, you can ask whatever the parameter if you want understood any calculations, and you can ask the doubts and I will send the solution for that one. Thank you.